Hello everyone. I'm sorry I have to be gone today, but we're going to continue on regardless. Yesterday we completed the analyzing lines of fit investigation. We were investigating the rise in the Earth's temperature associated with global warming, and you then did the corresponding population investigation. So hold on to that. I will look at that when I get back. And today we are going to be finishing out the unit for chapter 3 and 4 by starting section 4.7. So if you would please have your note packet out to section 4.7. If we need to pause the video now until everyone's ready, go ahead and do so. However, I'm going to start assuming that we are ready to go. Today we are looking at something called an inverse function. To start, I'm going to give a scenario that we can use as our framework for the rest of the discussion, and it has to deal with a biology scenario. So biologists have found that actually the number of cricket chirps per minute is a function, it's actually a linear function, of the outside temperature, meaning that there's a relationship between the two and they're related by an equation. The function is shown in the equation below. We're going to use this function just to first calculate the following and interpret what they mean to get some background. So the first one asked me, well, what is C of 75? Meaning I need to put 75 in for T, which is the temperature. So if I put 75 in for T, I'm going to get 4 times 75 minus 40, which is 4 times 35, which is equal to 140. What this means is when I put 75 in for T, C is equal to 140. What does it mean? And when it asks you to interpret it, it means you need to write a statement in English. So this would be when temp is 75 degrees, this is in Fahrenheit, the chirp rate is 140 chirps per minute. Now we're going to do it for 40. I need to put 40 in for the T. I then end up with 4 times 0, which is equal to 0, which means when the temp is 40, my chirp rate is going to be 0. So now I'm going to write a sentence for that. When temp is 40 degrees, the chirp rate is 0. The cricket stops chirping, it's too cold. So you can see as the temperature increases, the chirp rate also increases. As the temperature decreases, the chirp rate decreases, and then this model starts to break down once we hit 40. If it's below 40, no longer follows an equation. But once it's 40 or above, it follows a pretty linear situation. Okay? Biologists also find it useful to be able to count the number of chirps and then use that to calculate an estimate for the temperature, so the reverse. The way that this original equation was set up was I would supply some temperature and it would return a chirp rate. It'd be maybe more interesting if I could be outside and count the chirp rate and then estimate the temperature without using a thermometer or an app on my phone. Well, how would I do that? I need to convert this equation that's solved for C and actually solve it for T. So I need to solve for T. Then I have an equation where I supplied a chirp rate and it would output for me a temperature. So how am I going to do that? There's a few things. I could divide by 4 first. I could distribute the 4 and then solve. It doesn't matter. Most of the time when we've been solving, we've distributed first, so might as well do that. I get 4T, then minus 160. Then add the 160 over. I get C plus 160, then equals 4T. Now I need to divide everything by 4. Divide by 4, divide by 4, divide by 4. So I could write it two ways. I could actually write this as, I'm going to write T first. The temperature is equal to C divided by 4 plus 160 divided by 4 is 40. You might also see it written as C plus 160 and then all of that divided by 4. Either one of these would be perfectly acceptable ways to write the equation. But the goal is to get T solved for. Now I give it a chirp rate and I can calculate a temperature. It looks like I chose to do the first one. So when I solve it, my inverse equation, this is called the inverse. It's an inverse because the roles of the inputs and the outputs are switching. That's what an inverse function is. So vocab word of the day, an inverse function is a function that switches the roles of the inputs and outputs. So originally I gave it T and it supplied C. So originally T was an input and C was the output. Now it's the opposite. C is the input and T is the output. You will, if the book was writing this inverse equation, this is how we would write it. We would write it as C and then we do a -1. That's how we communicate inverse. I will explain why the mathematics community chose that when we study exponents. It will make sense then, but for now, just trust me that if you see a negative exponent in function notation, that's how we write the inverse function. So we'd say the inverse function for the chirp rate and temperature situation is equal to x divided by 4. X just stands for your input. We know in this case for the inverse function, that would be the chirp rate. We take it, divide it by 4, and add 40. This is how we would write the inverse function in function notation. We're going to do the following, just practicing interpreting how function notation works with regular functions and then with inverse functions. So the first one, for my regular function, if I gave it 60 and it output 80 for me, what do these mean? Well, in the original function, T was the input and C is the output. So this would mean when temp is 60, chirp rate is 80, this is 60 degrees, 80 chirps per minute. However, now if we have the inverse, this 16 is no longer a T, it is actually a C. And then it outputs for me the temperature. So how would I interpret this? This would be when the chirp rate is 16 chirps per minute, the temperature is 44 degrees. Hope you realize the key idea is the inputs and the outputs flip. If you want to, you could check this, for the inverse one. If I put 16 in for my input, I should get 44 for my output. Let's go check it. If I put 16 in here, 16 divided by 4, well, that's 4. 4 plus 40 makes 44. So that's exactly what we said. When we put 16 in for my input, which is a C, really, in my inverse, I get a 44 for my output, which is the temperature. I'm going to give you a chance to try how these inverse functions work. So you need to pull out your whiteboard. And my question to you is this. Based on the following relation and our definition for what an inverse function does, make a table for the inverse relation and plot the points from both tables. So this is the original functions table. This is the inverse functions table. And then I'm going to ask you, what do you notice? So here's the original. Make the inverse table. When you're making the inverse table, use the definition of what an inverse function does. It's a function that switches the original inputs and outputs. So pause the video now. Give everyone a chance, maybe minute and a half, to make the inverse table and then plot both the original table and the inverse table on the same graph. And I'm asking you, what do you notice? So pause, come back once everyone's had a chance to try. Okay, here we go. Let's make the inverse table first. Well, the definition of the inverse is it flips the inputs and outputs. So for the original table, if I give it -4, it's going to return 0. But for the inverse, it needs to be the opposite. It means if I give 0 as the input, it's going to return -4 as the output. Over here, if I give it 1, it will return -1. If I give it 2, it will return 2. If I give it 3, it will return 5. Now I'm going to plot both. For the original, it would be -4, 0, -1, 1, 2, 2, 5, 3. Draw my line in. It looks like that. For my inverse, it'd be this one. -4, 1, -1, 2, 2, 3, 5. And then graph it. And then this would have been a little tough, but maybe some of you notice that actually these two lines are a reflection of one another, and they are reflecting across the line y equals x. Why are they reflecting across y equals x? Because I told you that inverses flip inputs and outputs, and so y equals x would be the line that no point would be reflected across. So look at 2, 2. That point didn't change because if you flip 2 and 2, it stays the same. So y equals x is where your mirror is located. Otherwise, all these points get reflected to the other side. So this got reflected, these red. then this got reflected across. This stayed on it because it was on it, and then this got reflected across. So a original graph and an inverse graph, when you graph them, they are reflections of one another across the line y equals x. Why is this so? The reason is because inverses flip inputs and outputs. So the only points that won't get altered are any points that are on the line y equals x. If you are on the line y equals x, then you're going to stay on that because you're on the mirror. So the reason why this happens is because inverses flip inputs and outputs. Now we're going to practice using that skill. If they give us an original graph, can we sketch what the inverse would look like? Are there any good strategies? Well, let's use the strategy we just had. Let's do it by making tables. So step one is going to be make a table for the original, then make a table for the inverse. Then sketch the inverses, and you'll notice it's a reflection across y equals x. So here's the original. Well, I need to pick some points here. So get a few points. 4 is good enough. So the first one, 1, 2, 3, 4. So -4, -3, -2, -1, 1, 2, 1, 2, 3, and then 3, 4. There are some original points. Now what the inverse points would be the inverse. Flip them. -3, -4, -1, -2, 2, 1, 4, 3, and plot those. -3, 1, 2, 3, 1, 2, 3, 4. -1, -2, 2, 1. 4, 1, 2, 3, 4, 1, 2, 3, and then sketch this in. And if you notice, these ones don't cross. When you graph the inverse, they don't necessarily have to cross. Most of the time they will. The reason that this one doesn't cross is because if you sketch in y equals x, you'll realize that both these are parallel to it, so that when you reflect, it'll just be straight across. Neither graph has a point on the reflection line, so that means those graphs are never going to cross one another. So what's the strategy? Make a table. Making a table for this makes it much, much easier. Okay. Last one is, so we know how to find the inverse from a graph. Now we need to know how to find the inverse if I'm given an equation. So step one is going to be solve for your original input, just like we did with the cricket chirp and temperature, and then we need to rename it in function notation. I'll talk about why here once we get our first example. So find the inverse of each function. So it might be wise to rename f of x as y first. It makes it easier to solve. So I have y equals 5x minus 3. If I want to find the inverse, I need to solve for x now, because then I'll give it y as the input and it will return x as the output. So I'm going to add 3. I get y plus 3 then equals 5x. Now I need to divide everything by 5. Divide by 5, divide by 5, divide by 5. I then get 1/5 y plus 3/5 equals x. And that is the inverse function. Now I need to rename it. The reason that we rename it really has to do with being able to graph this on graphing calculators. If you pull out your graphing calculator and you go up to y equals, if I want to type the equation in for a line or any function, I always need the variable x. So if I go to the very first one, what was the original equation? The original equation was 5x minus 3. And if I go to graph, it will sketch that graph in. But you'll notice when I hit the variable, it always needs x. So we rename this so that in function notation, my original input's going to be x. But that's really only so I can graph it in a graphing calculator. So when I rename this in function notation, this is what we'd say. We would say for the function f, its inverse, when I supply an input of x, x just stands for any input symbol. We know because it's an inverse, the input really is y. We would need to type in a graphing calculator or a computer or whatever, 1/5 x. Again, x just stands for input. We know it really is y because this is an inverse situation, is 1/5 x plus 3/5. And this would be the inverse in function notation. Now I can type this in, 1/5 x. So I go back to my y equals. Because it's a fraction, I do 1 divided by 5, and then I need to use x because it doesn't have an input symbol for y. It wouldn't be able to do that. Plus, and then the other part was 3/5. So 3 divided by 5 in parentheses, and then when I graph this, and actually I'm going to put y equals x in there just to show that middle reflection line. There's the inverse, and then there's y equals x. It runs right between them. I see that this has the reflection property. So there's the first one. So step 1 was we just solve for x, and then all this step is a renaming step. There's no mathematics that went on. We just renamed it in function notation. We said f's inverse, when I supply an input, x is just standing for the phrase input here. We really know it's a y because it's an inverse, is 1/5 input plus 3/5. Okay, let's try one more. Put y in to start. 3/2 x minus 9. I want to solve for x. I'm going to add 9. Add 9 equals 3/2 x. Now I need to divide by 3/2. But how do I divide by 3/2? Well, I really multiply by the reciprocal. So I multiply both sides by 2/3. 2/3 times 3/2, that's just going to make the number 1. Now I need to distribute here. I get 2/3 y plus 2 times 9 is 18. 18 divided by 3 is 6. I end up with x. This is the inverse equation. Now I need to write it in function notation, so I just need to rename. When I rename it, I'm going to say this. Say f's inverse, when I supply the input, is equal to 2/3 times input plus 6. This is the inverse function in function notation. But all that happened here is just a renaming. We rename it so I could check it in a graphing calculator. So if you went to your graphing calculator and typed the information in, you typed in the original, which would be 3/2 x minus 9, and you typed in this function notation in blue, you would find that they are reflections of one another across the line y equals x. So step 1, solve for your original input. Then you'll notice your inputs and outputs flipped roles, and then we just rename it so it's in function notation. I could graph it in a graphing calculator. I'm going to ask you to try. So your goal is to find the inverse of each function. It might be good to first rename the f of x as y. Give everyone maybe 2 minutes to try these. Once you get your answer, check with a neighbor, and then unpause the video to see how you did. Okay, I'm going to go pretty quick through this. This would be y equals x plus 5. To solve for x, I just need to subtract 5, so I get y minus 5 equals x. Now I just need to rename. We would say f's inverse, when I supply the input, is equal to the input minus 5. That is it in function notation. Original in red, the inverse in blue. Second one, I'm going to rename it y just since there's less than to move around. 1/2 x minus 7, add 7, equals 0.5x. Then divide everything by a half. Well, dividing by a half would be the same as multiplying by 2, so I'm actually just going to multiply everything by 2. Multiply by 2. That's going to give me 2y plus 7 equals x. And this is the inverse equation. I'm just going to rename it using function notation. I would say the function's inverse is equal to 2 times the input plus 7. All that happened here is a renaming. We need to use x because the computer calculator only allows us to use x as the symbol for input. X is the symbol for input. It just kind of gets a little backwards when we're talking about inverses because inverses inherently flip inputs and outputs. So, but that is it for 4.7. If you would like, let's see if I can find the answers here. We're on section 4.7, and that's the last one in your assignment sheet. The answers are right here. If you'd like to leave the video paused, you can check your answers as you work. Feel free. Most of them are odd, so you can check in the back of the book anyway, but have your questions ready, and I will answer them when I get back. Thank you, and have a good day.